Can anyone hear me?
I don't have any questions on the test.
All right. There's no question, then we go directly to the lecture, which will be on power series, derivatives, integrals, sums, and the binomial series. In the first part, we are going to talk about the power series of a function that is centered at A. Last time we had the Taylor polynomial centered at A, and the power series will be the representation of the function in the form f of x equals sum k from 0. Let's say we could say actually it's k from 1 to infinity. And here you get the kth derivative at A divided by k factorial times x minus a, exactly the way we did the Taylor polynomial. And then we'll have to find the interval of convergence. Which is the set on which the series is equal to the function. Now notice the difference between this and the Taylor polynomial is that you're taking those derivatives all the way to infinity, and you can only do that if you have a function for which you can take infinitely many derivatives, right? Example 1, let's say we have the function f of x equal 1 over 1 minus x. If we are taking a equals 0, when a is equals to 0, we talk about the Maclaurin series, because right now this function we already know is equal to sum k from 0 to infinity x to the power k. So we know this from geometric series, right? And then we know that that equality is true for absolute value of x less than 1. So this is the interval of convergence of that series. On this interval, this function is equal to that, which also means that according to that formula, that the kth derivative at 0 divided by k factorial equals, what's the coefficient here?
1.
1. So that's what this means, among other things. Which means that the kth derivative of the function at 0 is equal to k factorial. So sometimes this formula can be used to find the derivatives of the function. You can see that we know this here without having to take k times the derivative of the function, just by looking at the formula of the series. We can determine what the derivative is equal to. Just as we could start by the function, find the derivatives and plug them into this formula to get the power series representation. Does that make sense? So let's say number 2. Let's say we get f of x equal e to the x, and we take a equals 0 also. This is also the Maclaurin series. Now tell me, what is the derivative of e to the x? And
e
here,
to the x.
second derivative.
That's also e to the x.
Third derivative.
Also e to the x.
So no matter how many derivatives I take, I'm always going to have e to the x, right? And therefore, right here, the kth derivative at 0 is going to be e to the 0 equal 1 for all of them. Therefore, so this is one of the exercises that you must be able to solve for your next test. Be able to take a function, get the derivatives, get a formula for the kth derivative at a point, and plug into this formula to get the Taylor series. And so here also you got this is also equal to f of 0, which is 1. So e to the x is equal to sum k from 0 to infinity x to the power k over k factorial, because that is 1 over k factorial. So this is what you get. Now we know that e to the x can be written as this, and now we need to find the interval of convergence. And for the interval of convergence, we have here ak is 1 over k factorial. Ak plus 1 is 1 over k plus 1 factorial. And so ak plus 1 over ak is k factorial over k plus 1 factorial. And this is k factorial over k factorial times k plus 1, which is 1 over k plus 1. Therefore, limit as k goes to infinity of ak plus 1 over ak equals limit as k goes to infinity of 1 over k plus 1, and this is 0. And because this limit is 0, that means r equals infinity. And if r is infinity, then the interval from negative infinity to infinity is the interval of convergence. Which means if the interval of convergence is from negative infinity to infinity, it means that for all x, for any real number, e to the x is equal to that. Therefore, for any real number x, e to the x equals sum k from 0 to infinity, x to the power k over k factorial. So no matter what x is, we can replace e to the x by that. And the other thing is we actually need to memorize these functions that I'm deriving in class. Okay, so that's the example for e to the x. Now let's look at another example. Let's say we take f of x equals sine x. Now, and then we also take a equals 0. So we are also having the Maclaurin series. Tell me here, what is the derivative of sine x?
Cosine x.
It's cosine x. Second derivative,
Negative sine x.
good, negative sine x. Third derivative,
Negative cosine x.
negative cosine x. Fourth derivative,
Sine x.
sine x. So you can see that when I started with the function sine x, after 4 derivatives, I am back to sine x. So I don't need to take more derivatives because I'm going to be getting the same thing repeating. I'm going to have the same thing that will be repeating after every 4 numbers, right? So I just need to know the value for the first 4 terms and I can conclude for the others because they are going to be same. So this repeats. So all others are going to repeat from here. Now, f of 0, sine 0 is 0. F prime of 0, that's cosine of 0, that's 1. Second derivative at 0, negative sine of 0, that's 0. Third derivative at 0, that's negative cosine of 0, that's negative 1. And then we start repeating. From here, after this, we repeat. And this shows that what? 0, 2, 4, 6, 8, 10, 12, 14, 16, and so on are all going to be zeros, right? So all even terms are going to have coefficient 0. And the odd terms are going to be 1, then minus 1, 1, then minus 1, 1, then minus 1. Which is the reason why this whole thing would be sine x equals sum k from 0 to infinity, negative 1 to the power k. That would be when k is 0 for the first term, that will be 1. For the second term, when k is 1, that will be minus 1. So we match it. And then it continues 1, minus 1, 1, minus 1. And then that'll be x to the power. And here, you're going to get 2k plus 1 for the first derivative. K is 0, so it's x because first derivative. For the third derivative, k is 1. And we have third derivative goes with x cubed. That's why it's x to the power 2k plus 1, 2 and k being 1 to justify that. And then divided by the factorial of the power you have here. Remember, the formula is sum kth derivative at a, x minus a to the power k over factorial k. So the factorial always goes with the power that you have. That's why we get factorial 2k plus 1, because we got the power 2k plus 1. And now this incorporates the fact that all the even ones are 0, because there's no even power here. You can see there's no even power, right? All right, so, and now the question will be, what would be the interval of convergence? This thing is technically x minus x cubed over 6 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial plus and so on. That's what it means. And what we got for e to the x was 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial and so on. Now, what's the interval of convergence of this one? You can say AK. Let me take absolute value of AK in that problem is 1 over 2k plus 1 factorial. So absolute value of AK plus 1 is 1 over 2 times k plus 1 factorial, which is 1 over 2k plus 3 factorial. Absolute value of AK plus 1 over absolute value of AK, that's going to be 2k plus 1 factorial over 2k plus 3 factorial, and this is 1 over 2k plus 3 times 2k plus 2. That's what you get when you simplify, because this thing is 2k plus 3 times 2k plus 2 times factorial 2k plus 1. And thus, you get limit as k goes to infinity, absolute value of AK plus 1 over absolute value of AK equals limit as k goes to infinity, 1 over 2k plus 3, 2k plus 2, and that's 0. And this also means that R equals infinity, and that leads to interval of convergence negative infinity to infinity. So also as for e to the x, for all x real number, sine x is equal to sum k from 0 to infinity, negative 1 to the power k, x to the 2k plus 1 over 2k plus 1 factorial. And similarly, we can get cosine of x equals sum k from 0 to infinity, negative 1 to the k, x to the 2k over 2k factorial for all x. So we get this the same way as we did the previous one. We show this one, that cosine x is equal to this. And that cosine x is exactly 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. Any questions? Do we have any questions on this?
No.
All right. Now we had e to the x, we have 1 over 1 minus x. And we have cosine x and we have sine x. Now, let me ask you this. How would you say, what would you say about this one? This, we can say this is example 4. If I ask you, how would we get e to the minus x? What would you say? Any guess?
Would it be the sum from k equals 0 to infinity of x to the negative x over k factorial?
X what? I didn't get.
X to the negative k over k factorial.
No. That's what changes in this function. What's the relationship between e to the x and e to the minus x?
They're reciprocals.
Apart from that, how do we obtain e to the minus x from e to the x? From the function e to the x? Replace x by minus x. So that's what you would do to get the Taylor expansion or the Taylor series of e to the minus x. Just replace that from x by minus x. So that is sum k from 0 to infinity. Replace x by minus x. That's it. And that will also be for all x real. So this is an operation that is valid for power series. You can substitute in a power series something. And if this is true and the other one is true, let me ask you a strange question. Let's see an example. 6. If I1 f of x equals sine hyperbolic of x, how do you think I would find the powers, the Maclaurin series? If I don't want to do the work from scratch and take derivatives and plug in and find the formula, and I want to use these things, how can I get that? And so this would use the fact that you can add, subtract power series on the same when they are defined on the same interval. So here, sine hyperbolic of x is e to the x minus e to negative x over 2. So I can subtract the two series. So that's 1/2 sum k from 0 to infinity x to the k over k factorial minus sum k from 0 to infinity minus 1 to the k x to the k over k factorial. And we can add this to get that this is sum k from 0 to infinity x to the k is the same, so we can combine them, and that is going to give us 1 minus negative 1 to the k over k factorial times x to the power k. This is what it is. And now we can simplify this thing. We can simplify this. How? Let's say here, we look at this 1 minus negative 1 to the k. When k is 2n, for example, negative 1 to the k is 1, right? 1 minus 1 is 0. When k is equal to 2n, this says 1 minus minus 1 to the k equals 0. When k is 2n plus 1, 1 minus negative 1 to the k equals negative 1 to the k is minus 1, so this is 2. So when the power is even, we get the coefficient 0. When the power is odd, we get the coefficient 2 over k factorial. So this thing and the 2 we have here will cancel this 2 to give off f of x equals sine hyperbolic of x is nothing but sum n from 0 to infinity, because I'm replacing k by 2n or 2n plus 1, n beginning from 0. And that is going to be x to the power 2n over 2n factorial. So, and that's 2n plus 1, sorry. So it's sum x to the power 2n plus 1 over 2n plus 1 factorial. All right. So this is how you can work with power series. You can add them, you can combine them when they have the same powers, you can add the coefficients. And the same way we can find cosine hyperbolic of x. So similarly, we have cosine hyperbolic of x is e to the x plus e to the minus x over 2. And you work it out similarly, you're going to get sum n from 0 to infinity x to the power 2n over 2n factorial. And then you can also see that cosine hyperbolic of x plus sine hyperbolic of x is nothing but e to the x. You can check that as well. Because here, this is sum n from 0 to infinity x to the 2n over 2n factorial plus sum n from 0 to infinity x to the 2n plus 1 over 2n plus 1 factorial. And on the other side, that's sum k from 0 to infinity x to the k over k factorial. And here is the sum of all even numbers, and this is the sum of all odd numbers. The sum of all even plus the sum of all odd gives the sum of all of them. And this equality is true by the definition of cosine hyperbolic plus sine hyperbolic. Any questions? Now, this is how you worked it out on each of the examples, the way I just showed you. Take the function, take the derivatives, right? Plug in. Let me give a last example on this so you don't think it's always going to be starting from 0. Let me take the same function, f of x equals e to the x, and all derivatives are e to the x, and then at the point a is going to be a e to the a. So all the derivatives are equal to e to the a, and therefore the function f of x is equal to sum k from 0 to infinity. The derivative is e to the a over k factorial x minus a to the k. So e to the x can also be written as sum k from 0 to infinity e to the a x minus a to the k over k factorial for any x and any a. All right, so those are our facts. Now, the other thing we had on our list for today was being able to take the integrals and derivatives. The sum, I just show you how you use the sum, right? Let me write that down again. Remind that again. The sum, k, from 0 to infinity, ak x minus a to the k. This sum is equal to sum k from 0 to infinity, ak plus bk times x minus a to the power k. That's how you add them. When they have the same powers, the same x minus a, you just add their coefficients. So and that if the first one was f of x and the second one was g of x, then the function is going to be equal to the sum of the two functions. And that will be through on the interval where both series converge, right? Now, the most interesting thing was, how do you do derivatives and integrals of power series? So if f of x equals sum k from 0 to infinity ak x minus a to the k, then the derivative of f of x will be sum k from 0 to infinity k times ak times x minus a to the power k minus 1. And we can drop the k equals 0 because when k is equal to 0, the first term is going to be 0. So that's how you take the derivative using the power rule. So if I know the Taylor expansion of the function f of x, if I want to find the Taylor expansion of the derivative, I don't need to actually take the derivative before looking for the expansion. I just take the derivative of what I have inside the power series. Does that make sense? Okay. So for example, for cosine and sine, we had this. We had sine. We had sine x equals sum k from 0 to infinity, -1 to the k, x to the 2k plus 1 over 2k plus 1 factorial, right? This is what we got. And so the derivative of sine x, which is cosine x, I don't need to go and look for the Taylor expansion of cosine x. I just go and I say it's sum, k from 0 to infinity, -1 to the k, and then derivative of x to the power 2k plus 1, that is 2k plus 1 x to the power 2k divided by 2k plus 1 factorial. So I just go in there and I only take the derivative of the power of x that I see. And that gives me cosine x equals sum k from 0 to infinity. And this is -1 to the k, x to the 2k. And notice that 2k plus 1 over 2k plus 1 factorial is 2k factorial. And this is exactly what we got as power series of cosine x. Notice that this time I didn't have to take any derivatives and plug anything in. I just used the fact that I know that the derivative of sine x is cosine x, and that allows me to find the power series of cosine x. All right? This thing can also be used backwards. If I know the power series of the derivative, I can go backwards and find the power series of the function. All right? In that case, that would be calling that the integral. It's still in that 3. So if I have f of x equals sum k from 0 to infinity ak x minus a to the k, then the integral of f of x dx is equal to sum k from 0 to infinity ak, and then I integrate x minus a to the power k. That becomes x minus a to the power k plus 1 over k plus 1, and then the constant of integration. And that's how you would find the power series of the integral. And then as you did in Calc 1, 2, if I know a specific integral that I need, I use the values to find the constant of integration. Example. Let's say here we have f of x equals natural log of 1 minus x, for example. I don't know how to handle this function, right? Then I'm going to say, okay, what's the derivative of this function? F prime of x is, the derivative is -1 over 1 minus x, right? That's the derivative of this function. Oh, after taking the derivative, I look and I say, hey, I know this function. 1 over 1 minus x. I know the power series. What is it equal to? What's the power series of 1 over 1 minus x?
1.
It's a power series, Amni.
Is it the sum from k equals 0 to infinity of x to the k?
Yeah. So that's negative sum k from 0 to infinity x to the power k. So this function is the derivative of that. Therefore, I'm going to say that the function f of x is equal to the integral of negative sum k from 0 to infinity x to the k, which is negative sum k from 0 to infinity, and the integral of x to the k is x to the k plus 1 over k plus 1. So that's it, plus a constant of integration. And now we need to find that constant of integration because we know completely the function f of x by plugging in any number that we want. F of 0, for example, if I plug in 0, ln of 1 is 0. So I know f of 0 is 0. That will allow me to find c. I plug in 0 here. I get 0 plus c equals 0. So c equals 0. 0, the first 0 is from here. When I plug in 0 here, sum k from 0 to infinity of 0, this is 0, plus c equal 0 from f of 0 equals 0. So I solve to get c equals 0, and I put it back there. And that tells me that natural log of 1 minus x is equal to negative sum k from 0 to infinity x to the k plus 1 over k plus 1. And I can change the variable here because k start by 0 and I have k plus 1. So I'm going to have it start from 1, and therefore I just have n. So I sum n from 0 to infinity x to the power n over n by replacing k plus 1 equal n. So this is what natural log of 1 minus x is, equal negative that sum. And we got that without finding all the derivatives of natural log of x to plug into the formula. We just got the first derivative, and we realized that it's a function that we know. And so we wrote the power series of that function, and then took the integral to get natural log. The same thing would happen for the function f of x equals tangent minus 1 of x, which we call arctangent of x. Please, you try this example. What do we say? Want to say something, Matthew?
Well, I got sum from k equals 1 to infinity.
Let's start by
X.
the beginning. What's the first action you have?
Okay. Well, the first thing I did was I took the derivative of arctangent.
Good. That's the first thing to do. Derivative. So what's the derivative equal to?
1 over 1 plus x squared.
Excellent. Which we can write as 1 over. Right?
Yeah.
Okay. So you got here what?
And I said that was equal to negative x to the 2x or to the 2k.
Negative x squared to the k. You are replacing x by negative x squared. And after that, you still have to work it out before getting to the other level. And now negative x squared to the k, it's not negative x to the 2k, it's negative 1 to the k first. And then x to the power 2k. And we have to be very careful with that. That's a pretty common mistake. Now, from here, you see, okay, I know the Taylor series of the derivative. Therefore, we take the integral. And this is sum k from 0 to infinity, and we integrate. We integrate x to the 2k, we get 2k plus 1 over 2k plus 1. And then we have a constant of integration. Yet we also know that arctangent of 0 is 0, right? So we use that value. And then the sum, when x is 0, this sum is 0. That will be 0 plus c equals, and arctangent of 0 is 0. So here you also have c equals 0. And therefore, you have arctangent of x is nothing but sum k from 0 to infinity, negative 1 to the k, x to the 2k plus 1 over 2k plus 1. Notice also that this somehow looks like, it somehow looks like sine, right? But the difference is that for sine, you have factorial here. Does that make sense? The big difference between arctangent and sine in the Taylor series is just factorial that you have on 2k plus 1 for sine. And also here, the other problem here will be integral of convergence. And it's not for all x's at this time. You got to check now and see. Interval of convergence, you got to figure out so A K here in absolute value, call this, that's A 2K plus 1 in absolute value. In this case, it's 1 over 2K plus 1. So A2 times K plus 1 plus 1. In absolute value, that's 1 over 2 times K plus 1 plus 1. It's 1 over 2K plus 3. And so limit as K goes to infinity of absolute value of A 2 times K plus 1 plus 1 over absolute value of A 2K plus 1. This is that function divided by this, and that limit is going to be equal to 1. So R is 1 over 1 equal 1. In this case, it is not true for all real numbers. Unfortunately, it's only true for x within R equal 1. And we can plug in the numbers to check the boundary. X equal minus 1. If you have x equal minus 1, you're going to plug it in here, and you're going to have sum k from 0 to infinity, negative 1 to the k times minus 1 to the 2k plus 1 over 2k plus 1. And minus 1 to the 2k plus 1 is always minus 1, right? So this is sum k from 0 to infinity minus 1 to the k over 2k plus 1. And we can show that this thing converges. And I'm not going to spend that time on it today. Converges as alternating series. And you understand what that means. So you have a Bn that is decreasing, limits 0 and positive. And the same thing works for x equal 1. When x is equal to 1, you get 1 there. So this was a minus 1 here. Because negative 1 to the power 2k plus 1 is minus 1. I just wrote the minus out here. And then the other point will be x equal 1. And you will have sum k from 0 to infinity, negative 1 to the k, 1 to the 2k plus 1, and that's always 1 over 2k plus 1. And this is sum k from 0 to infinity, negative 1 to the k over 2k plus 1. And you can see that this thing is the opposite of that one, right? This sum with a minus is the opposite of this one. And this also converges, therefore, as alternating series. And so my question, does this agree with the things that we know about arctangent? This means that arctangent of -1 would be the opposite of arctangent of 1. Is it true? I mean, that's true because arctangent of 1 is pi over 4, right? And arctangent of -1 is negative pi over 4. Are we good? All right. So here, this converges, that converges, and so interval of convergence is 1, -1 less than or equal to x less than or equal to 1. Any questions? So now we have learned how to use the integrals and the derivatives to find power series of functions. Let's get this one. You could say some of the application will be fine. This I will ask you to find this sum, for example. What do you think this sum is equal to? I would say here, this is nothing but e to -1. And the only way you can answer this question is that you know the power series that we have derived in this class. Because if you don't know them, you can't see what the answer is. The power series of e to the x is sum of x to the power k over factorial k. So this is e to -1. If we want sum k from 0 to infinity 1 over k factorial, I would say right away this is e, because on top there, that's 1 to the power k over k factorial. If you say find sum k from 0 to infinity, -1 to the k over 2k factorial, and I say, okay, -1 to the k, something is missing here. What is that? It's 1 to the power 2k. So this is nothing but cosine of 1. Okay. It will get sum a from 1 to infinity it, what could be here? One half to the k, for example, over k. What would that be? Then you would think of what we just got as sum for natural log. We figured that natural log of 1 minus x was negative sum x to the n over n from 1 to infinity. So this thing here is nothing but negative natural log of 1 minus 1 half, which is negative natural log of 1 half, which is natural log of 2. Which also in some ways means that actually natural log of 2 is nothing but sum k from 1 to infinity, 1 over k times 2 to the power k. All right, so those are some of the applications that you might see here and there. Is there any question? Nope. All right. So you can look for this exercise before doing your homework. Find the formula for binomial expansion. It's in that book. And we can stop here today. Thank you for coming.
Thank you.
Thank you.
Thank you.